Before we get into today's meat, I want to quickly talk about lexicographic ordering, how words appear in the dictionary. The compare function, when we give it apple and apple, will return 0. That means both words are exactly the same. If we call it with apple and apply, we get an arbitrary negative number because apple would appear before apply in a dictionary. Why negative 20? Because e minus y is negative 20. Okay. And if we compare apply and application, we get an arbitrary positive value, y 16, because y minus I happens to be 16. Okay, and if we compare apple and apple pie, then we get negative 3, y negative 3. So the apple is a prefix of apple pie, so we can't subtract characters here. So instead, we simply subtract the length, and pi is 3 longer than nothing. That's why we get negative 3. But any other negative value would have been fine, and any other positive value would have been absolutely fine. Okay, and today's problem is basically lexicographic ordering with some extra step. Nested lexicographic ordering with type promotion, I call it. Let me explain what I mean by that. So here we have lists of numbers, and we can pretend that the numbers are letters. So 1 would be A, 3 would be C, and 5 would be E. And if we compare these two lists, then we would say the first list is smaller than the second list, or comes before the second list, because this word would come before this word in a dictionary. So I'm not talking about the length here when I say smaller. I'm talking about lexicographic ordering. Here we have a problem. So the list 2, 3, 4 compared against the single value 4 is a type error, if you will. So the rules state that we wrap the 4 in an implicit vector, and then we would have the words B, C, D, and D. And of course, B, C, D would appear before the D in the dictionary, right? Here the other way around. 9 wrapped in a vector would be the word I, and I would come after H, G, F in a dictionary. Here we have the common prefix, but the second list is longer, so DD comes before DDD. Here's the other way around. GGGG would come after GGG in a dictionary. Then some tricky cases. The empty list is a prefix of the list containing 3, and this empty list is a prefix of the list containing an empty list. That may be a bit confusing, but it will just work with our code. Don't worry too much. And here the 7 is bigger than 0, of course. Okay, so let's look how I encoded everything in Clojure. So here's our compare values function. Given a left and a right value, we shall compare them. We use the cont macro to check which of the cases do we have. Are they both numbers, for example? If they are both numbers, then we use the simple built-in compare function, which will return negative number, 0, or positive number. As we saw with strings, it also works with numbers. Okay, if only the left is a number, then we try again, but wrap left in a vector. If only right is a number, we try again and wrap right in a vector. And otherwise, we simply assume that both are vectors. So keywords are truthy, and that will trigger this case. Okay, so what do we do here? So we map our compare values function recursively over left and right. And then we will get a sequence of comparison results. And we're not really interested in the zeros. So that would be the apple and apple pie case. For example, we want to skip everything. Or in the apple and apply, at least we want to skip the first 4 characters. And then we're interested in the first comparison that isn't 0. So hopefully negative or positive. This could return nil if one of the words is a proper prefix of the other. Why is that? So if you look at map, it will work until any one of the collections is exhausted. So if one is a proper prefix, then we get nil. If we get nil via the OR macro, we will subtract the length, just as we did with the apple and the apple pie. Right, but it's very important that you only look at the length if all the comparisons before that were indeed 0 and no non-zero value was found. Right, and then for part 1, what do we do here? So first we partition into partitions of 2, so pairs of those packets basically. And then we call a very helpful function called keep indexed that is similar to the keep function, the opposite of filter, which will not only pass us the current element, which we destructure into left and right here, but also the index, because we're interested in the indices. Okay, so we pass left and right to our compare values function, and if it's negative, then the order is already correct. Left comes before right. If that is the case, we want to keep the index, but we we increment it because the indices start at 1 in our puzzle and not at 0. Okay, and numbers are truthy no matter which number it is, and if the comparison isn't negative, then if will implicitly return nil because we have no else case here, and the element or index will be thrown away. Right, and then we add up all the interesting indices, which will give us 13 in our example. Okay, and then for part 2, we have 2 additional packets here, vector, vector 2 and vector, vector 6. We put them into our input and then sort them according to our criterion. So the sort function has an overload that accepts a comparator here. That's quite useful. And then we want to know where these packets ended up. So we call the keep index function again. We're given the index and our packet. And then we want to know if the packet is one of those divider packets. So we simply pass the packet to the set divider packets. Yeah, so why does that work? So I prepared a little something here. If we have a set like hello world, that's a persistent hash set, and we call it like a function and pass it hello, which is contained, then we get hello back. Whereas on the other hand, if we pass it goodbye, then we get nil back. So yeah, it basically tells us if the element is contained, because strings are truthy and nil is falsy, of course. Right, so only the packets will survive. We keep their incremented index again, and then we shall multiply the indices starting at 1.